for participating in this second ANCHISE talk concerned with what can nanotechnologies do to combat the illicit trafficking of antiquities. It's the second of the 3 rounds. The next one is expected soon, and of course we hope today to stimulate your interest in order to follow also this third step. In the audience today, I see some people that has already attended the previous webinar, some other people that is also going to come to Brussels next week when we will celebrate the first forum of the project. But now today, let's focus on the ANCHISE talks. I don't want to spoil time. I give the floor to Irene, who is our guru for everything that is happening on ANCHISE, and she will provide us with some general information before giving the floor to Jérôme and Armando. Please, Irene, the floor is yours.
Thank you very much, PG. So, dear participants, fellow researchers, members of the ANCHISE Consortium, partners of a project, and friends of our institutions, thank you for joining us today. This is the second ANCHISE talk. I'm Irene Zaitsev, the project manager of the ANCHISE project within the École Française d'Athènes, the coordinator of the ANCHISE project. Sadly, Professor Véronique Shankowski, the coordinator of the project, is participating in another conference right now and will not be able to attend. If you are joining us today for the first time, ANCHISE, which stands for Applying New Solutions for Cultural Heritage Protection by Innovative Scientific, Social and Economic Engagement, is a Horizon Europe project aimed to fight against the looting and trafficking of cultural goods in Europe. ANCHISE started in early 2023 for 3 years, along with 2 other projects of its cluster, Aurora and Enigma, crossing the methodology of networking that has proven its efficiency in the Horizon 2020 NetShare project. ANCHISE aims to develop a comprehensive and replicable response to the challenges of effective protection of cultural heritage in Europe through the development of technological solutions. However, ANCHISE is also a symbol, who you probably know. He is the father carried on the back of his son Aeneas out of the crumbling city of Troy. These names recalls us the duty we have to protect our cultural heritage. In this shared fight for the protection of the European cultural heritage, the ANCHISE project is joined by 15 following partners from all over Europe. The project aims to strengthen the link of a community based on our shared will to fight the looting and trafficking of cultural goods, and to develop a toolkit of innovative technological solutions to be used by the various involved partners, researchers, actors from the law enforcement services, art dealers, and other professionals from the private and public sectors involved in new technologies. So among this very rich community, the researchers that we are listening to during the ANCHISE talks are experts on the use of technologies within our field scope of action. The speakers we are delighted to be hearing today within the second session of our webinar series are Dr. Jérôme Plein and Dr. Armando Fernandez. Dr. Plein is the director of the Laboratory Light, Nanomaterials and Nanotechnologies at the University of Technology in Troyes, France. He is a recognized expert in nanostructuring, nanofabrication, nanoconstruction thematic, and in the application of nanoparticles in the field of nanoptics. Dr. Plein is the author of a book chapter entitled Nanofabrication for Plasmonics. He supervised more than 20 PhD students and authored and co-authored more than 100 papers in referred journals. Finally, Dr. Plein is in charge for the regional NanoMat platform dedicated to nanofabrication and nanocharacterization of materials. Dr. Plein will be co-hosted by Dr. Armando Fernandez, as we mentioned previously. Dr. Fernandez is a member of the ANCHISE Consortium within the INOV company. Dr. Fernandez is specialized in physics engineering. After gaining a PhD entitled Forest Fire Detection by Analysis of backscattered lasers radiation from the Instituto Superior Técnico in Lisbon, Portugal. Dr. Fernandez participated in 12 scientific projects within national or international funding and has been working in machine learning since 2001 and hyperspectral spectroscopy since 2009. He is currently working with the INOV company in Lisbon as the principal researcher in the project ResNet Detect that aims at creating an automatic wildfire detection system. Within the scope of ANCHISE, Dr. Fernandez participates in the development of a tool aimed to identify paper through spectral fluorescence signature. We are all very grateful to be hearing you today and to discuss together what can nanotechnology do to combat the illicit trafficking of antiquities. So, after Dr. Plan's intervention, we will be hearing Dr. Fernandez's question and we'll have an exchange session. Thank you very much. Jérôme, I give you the floor.
Thank you. So first I will share my screen, the good one. I think that this one is the good one. Normally it works. Yes,
it works.
it's okay?
Yes, yes, yes.
Perfect. So, hello everyone. I'd like to start by thanking the organizer of this series of conference organized by the ANCHISE project. So I'm Jérôme. I'm currently a professor at the Université of Technologie, and I have to correct you, Irene, because I'm not the director of the light, nanomaterials and nanotechnology lab. I'm just one of the researchers of this lab. So I prefer to correct it because if the director is online, I will not have some issues with this guy, you know. But by the way, I'm the deputy director of UTT, so the general deputy director of UTT. So maybe it's not really clear on my bio. So I assume the fact that all the people online today were not specifically specialists in nanotechnology. So I'm going to give you a brief introduction to nanotech and its application in everyday life. So first, I will present you the plan of my presentation. So the first part will be dedicated to what are nanotechnologies, then areas of application of nanotechnologies, and then I will finish and I will present you the nanolabeling and the opportunities that nanotechnology will offer to safeguard archaeological artifacts. So let's begin by the beginning. So what are nanotechnologies? And okay, I love this schema because okay, you have here the things. So basically we are situated here, and nano is here, okay? And nanotechnology, I give you some definition, is the development on practical use of structures and devices on the nanometer scale. Let's say when we get one dimension between 1 and few hundred nanometers, then you will find many definitions. This is mine. And okay, we have different definitions. And then when we speak about nanotechnology, we refer to the creation of useful materials, devices, and systems by manipulating the matter at the nanometer scale with characteristic dimensions of less than 100 nanometer. This reduction of the size will allow us to exploit new phenomena and new properties specific to this small scale. So I will quickly give you some things in order to be able to make the difference. This is a clue. The size, it's okay, basically in the range of the millimeter. So it's 10 to the 6 nanometer. Then here there is some pollen. The diameter, it's about 20 microns, 20 micrometers. In that case, it's only 20,000 nanometer. So we will reduce the size and we will get the red cell. So you know the red cell, it's part of your blood. And in that case, the typical size of the red cell is about 2.5 micrometers, corresponding to 2,500 nanometers. And here I present you a carbon nanotube. And the diameter of the carbon nanotube is about 2 nanometers, and the typical length will range from hundreds of nanometers to some microns, okay? But the diameter is around 2 nanometers. And just to let you know, the fact that reducing the size like this on the carbon nanotube will induce a Young's modulus of this structure, which is similar to that of diamonds, and the thermal conductivity of this carbon nanotube is improved by several order of magnitude if I compare with just graphene, okay? Or a graphitic layer, some graphitic layers. So then in order to continue with this kind of scales, let's say, so I present you here the living world. You know it, I guess. So this is the top, bottom-up approach. So we are going from very small things like molecules, then protein, then assembly of proteins. You know, this guy, it's DNA, then the cells, then we have the hairs. Oh, this is a small bug. I can't remember the name. Then okay, we increase the scale. So this one is 1 millimeter. And then when we increase the scale, we get butterfly right here between 1 and let's say 10, 15 nanometers. And finally, here at the meter scale, we have the human. And then we are here the human-made products. This the other way, so the top-down way. We have here at the size of the meter a car. Here is the cell phone. This is not considered a card, but just the chip. And the chip is okay. The typical size is about 1 centimeter. A microprocessor. Okay, between 100 micrometers to the millimeter. Then the phototransistor, 10 microns, nanotransistor, 100 microns, and now we are in that part with the nanotransistor, the last generation, we will find a transistor of about 5 to 10 nanometer in order to give you a real scale, a real time things. Then around 10 nanometers, we have the laser based on a quantum box. This is just an aggregate of atoms aggregates. And at the 0.1 nanometer, we have one single atom, okay? So it's just in order to give you some number, some scales, in order to show you the things. So basically, for me, the nano world is here. We are dealing with atoms aggregate, okay, all that things. And then in the living world, all that things. So small molecules, biggest one, and even bigger one, okay? So I will just mention that this is one of the first, or maybe the first transistor made or chip made by Intel in 1971. So in that case, this chip is made from 2000 something bipolar transistors. Okay, you can find here the things, and in its range, okay, better range of application, this chip is able to do 90,000 operations per second at a maximum frequency of 740 kilohertz. Okay, so 50 years later, we are here. This is the one of the last Core i9 things from Intel. In 2022. So in that case, okay, we have 32 cores. The size of the transistor, it's about 10 nanometers, and we are able to do 10 giga operation per second, okay, at the maximum frequency of 6 gigahertz. So it means that in 50 years, we are able to multiply or to increase the number of operations per second by 5 orders of magnitude, okay? And just here, I guess that you know that, but this is the second Moore's law. So he made a first law, and then he corrected it in 1975, if I remember well, and said that, okay, we will multiply by 2 the number of transistors onto the chip each 18 months. Okay, so it works pretty well, as you can see. So, okay, and the Moore's law is still okay. It means that, okay, we are able to reduce the size of the transistor and to integrate more or less much more transistor on the same size of chip. At this time, the chip was, okay, about 10 micrometer square, and okay, now we are more or less in the same range, but okay, the number of transistor was at this okay, and, I get that basically we are in that range at the beginning, and now the number of transistor is that. So 50, 10 to the 9 transistors. Just crazy. Why nanotechnology are very, very interesting? Because in the massive state, and I will give you a clear example just after, okay, we have a large number of atoms in the materials. So the properties are ruled by the atoms contained in the volume. At the nanometric dimensions, we have a few dozen of atoms, and in that case, the ratio between the surface atoms and the volume atoms is completely different, and the surface atoms will govern the properties. So I give you quick, very nice things. So we will consider one sugar cube. It's about 6 centimeters square of surface area. And now we will divide this cube into small part of 1 nanometer nanocrystals. And in that case, the surface area will be of about 600 square meter. So means that we have the same area than our rugby field. Okay, so that's huge, and that's really, really important difference. And this difference will induce a very, okay, an increase of the capacity and a diversity of physical, chemical, and so on properties, which is really, really incredible. So I present you this material called gold. Maybe you know it. And okay, this is bulk gold things. So you can see that here gold is goldish. And this is the gold I am dealing with. Okay, so here we have 2 nanometers nanoparticle of gold. So you can see that the color here it's goldish, and here it's okay, orange or orange brown, let's say something like this. So if we look the nanoparticles right here, we can see these things. So the image are obtained through transmission electron microscope. And we can see here the atomic plans. So the different lines you see on this image, okay? And okay, this is the things we have. We are able to find the structure, the atomic alignment, and so on and so on. Then, okay, we will increase the size of these small gold seed to, let's say, 12 nanometer. So we have this kind of nanoparticle right here, okay? They are bigger, and you can see that the color scattered by the solution. So basically it's water with gold nanoparticle, okay? And if you send light, you will scatter the light, and you will get the complementary light. In that case, you will find some pink solution, pink color, okay? So I will continue to increase the size till here. So here, maybe it will be about 60 nanometer in diameter. And then I will add some molecule in the solution. The molecules will contain the growth along different crystallographic direction. So it will not be possible for the gold nano things to increase in size, for example, in that way, and only in one direction. So in that case, we will get this kind of, let's say, nanorods. And then we will continue the growth of the nanorods. So the aspect ratio, so the ratio between the diameter and the length of the nanorods will change. So the light scattered by the solution will change to, scattered and absorbed by the solution will change to, and we will get, okay, this kind of thing. And here you can see that we have at the end this very nice, for these nanoparticles, this very nice purple color. So you can see that, okay, there is a quite strong difference between bulk gold and gold at the nanoscale, as we can see here. And then it's possible to see that just by playing with the size of our nanoparticles, so the number of surface atoms divided by the number of volume atoms, it's possible to tune under control the optical properties of the gold nanoparticles. So in order to get this kind of nanoparticles, basically, we have 2 ways to do it. The first one is called top-down. So we will start with a solid object, and then we will reduce the size, okay? We will shape it to get something smaller, so, like this guy. And then we have the bottom-up approach. So we are playing, in that case, with building blocks, and we will assemble the building up from the ground up, okay? So we have basically this kind of thing. If you are playing Lego, It's more or less the same. Okay? So I will begin to explain you how we are able to do this kind of thing. Generally speaking, and okay, now we can reduce the wavelengths or many things, but we are basically using light. Okay, the light now it's UV or extreme UV and so on and so on. And there are the techniques used in nanoelectronics in order to make the nanotransistor I shown you just before. So we have a reticle. It's like a mask, if you want, in order to mask the light. So then we have a lens. We will focalize it on the wafer. So this is the silicon wafer, and then we will make the different chips into the wafer. Okay. So we have a resist right here covering the wafer, so photoresist, and we will just print the replication of this mask in the photoresist. Okay. So basically it works pretty well. We are our limitation, which is the limit of diffraction. And in order to beat this limit of diffraction, we played with shorter wavelength. So from the, let's say, visible light, we are reducing it to the UV, extreme UV, or electrons. Doing this with electrons, we do the same. It's called e-beam lithography. So we are using this kind of machine. And we will get that. In that case, basically the approach will be more or less the same. So we have a wafer, we have then a layer of a resist. In that case, it's a PMMA. You know the PMMA. The commercial name is plexiglass. Okay, then we have an aluminum evaporation, but okay, it's not an obligation, and it will depend on the substrate you are using, but okay, it's more detailed stage. And then we will just expose the resist with our e-beam. So we will send electrons to the resist. The fact will be that, okay, we will break some polymer chains doing that, and then we have a development step. During the development, the smaller chains will be removed and the bigger one will stay onto the wafer. So we get these kind of things. Let's say finally it's just a nano pattern. And then we will evaporate metal, for example, because I was dealing with gold. So metal, let's say gold in that case, because it's yellow. And then we lift, so we remove the resist, and we get the things we realize in our mask. Okay? So I show you something we made a long time ago in the lab. So it's a nano semi-sphere, nano rods, nano triangles. So basically, using e-beam lithography, we are quite free to write the things we want because we are just moving some kind of electron pen, let's say, onto our sample. So we can design all the things we want, okay? So, okay, there are many other top-down approaches, but okay, basically, you get the trick. We make a mask, and then we will or transfer the mask to the substrate, or write through the mask, or directly make the mask using e-beam lithography, for example, and then we will evaporate a metal or another thing through the nano holes made on the mask. Okay? The second approach is the bottom-up. In that case, we will use chemical synthesis of nanoparticle solutions, and then we will assemble these nanoparticles into more complex objects. In that case, there is no need for expensive equipment. We are basically dealing with this kind of gold nanoparticles, just playing with some gold salts, water, and a microwave oven, the same than you have in your kitchen, basically. Yeah? And in 2 minutes, we are able to do a very nice solution of 12 nanometers gold nanoparticles. So it's very easy. As I shown you before, we are able to deal with different shapes. So in that case, we have different prism, triangle, and so on and so on. In that case, we are very nice, basically single or almost single crystals. So quality is much more better. Then we can add a layer, let's say a shell, in order to fabricate a core shell nanoparticle with 2 different materials. So in that case, for example, we will have gold nanoparticles covered by a shell of silica. Okay. And okay, then we can the same. I will not give you many examples, but it's possible to tune the size, shape. We are able to do tripods, Janus spheres, many things. Okay. And then deal not only with gold, but with silver, with aluminum, with copper, with many things, with cadmium, selenium, for example, and so on and so on. Then the problem when you're dealing with this kind of nanoparticle in solution is, okay, you have a solution with nanoparticle, but they are not organized onto the surface. So we developed this kind of approach. We're dealing with microspheres and our nanoparticles. Here we have a solution of both. We put this solution onto a substrate, and we are just to wait a bit. The solvent will evaporate, okay? And then after the evaporation of the solvent, we just remove the biggest nanoparticle with a tape, okay? And we will have this kind of things. So this is the print finally, okay, of the biggest nanoparticle, because the smallest one come like this. I will just make you something like this. So I have my big nanoparticle, and then the smallest one we will be coming right here, okay, around the big sphere, and we will be able that way to create rings. So we did it. We have some rings. Then this diameter, the diameter of the rings is given by the diameter of the sphere, and the distance in between both same is given by the diameter of the biggest sphere. So in that case, the spheres, these one are of about 2 micrometers. And you have to imagine that we have 2 things like this. Okay, and they are just organized like orange. Okay. So orange in my world is an hexagonal compact structure. And then we are able to combine both. So we will be able to develop hybrid approach. So making a mask, and then we will replace the step of evaporation by another way to deposit nanoparticles made by chemical ways. So I will present you something right here. So first step, we make the mask using e-beam lithography. Then we use a technique called small force. Basically, the things in that case we made is something like this. So we have the substrate. We have solid things right here. And we will have here, okay, a liquid with the nanoparticles. Okay, like this. And we will apply a flux like this. So we will push the green interface between air and here the liquid. And like this, it will be possible to fill the pattern we made previously. Okay, so first we designed the pattern using beam lithography. Then we played with these things in order to put it the nanoparticles. We remove then the blue pattern if you want, and we get that. So you can see that, okay, we have an Einstein here made of silicon nanoparticle. The silicon nanoparticle are in that case okay, in the range of 100 150 nanometers in diameter. Okay, they scatter the light in the blue range in that case. Okay, and these scanning electron micrograph of the structure, and this is an optical one. So you have a dark field microscopy, so it's using an optical microscope, and here it's an scanning electron microscope. Okay, in both. So you see that we are able to organize nanoparticles made by chemistry onto a substrate, even in a quite complex shape. Okay, now you are more or less specialist in nanofabrication, and I will present you the areas of application of nanotechnologies. So basically, you will find nanotechnology in all the different way of application. So the first one is ITC. In that case, you have surveillance and detection systems, optical signaling, displays. Okay, you will find it in electronic components, the photonic crystals, storage memories, processors. So you have all nanotechnologies in your pocket right now. In energy, with the energy generation, storage, catalyst, defense and security with monitoring system, detection of chemical and biological agents, more precise guidance systems, marking, cryptography. For material and manufacturing with functionalized textile, skin care and cosmetic, nanocomposite and surface treatment, like the self-cleaning windows and this kind of thing. In biomedical health, with the vectorization of drugs, biocompatible implants, miniaturized diagnostics. And then in agriculture and food, with the nano encapsulated nutrients. And whoops, sorry for that. Fractional packaging, specific sensors in environment too, with waste recycling, air and water pollution sensors, water filters. So basically, for example, in the food, you will find many nanoparticles in the powder. So if you buy some coffee in powder, you will have nanoparticle in order to avoid the aggregation first, and then to promote the mousse in French. I can't remember it in English. I'm sorry for that, but okay. Okay, the part the part when you have a cappuccino, the white part on the top. Okay, so using nanoparticles, you will be able to promote this kind of espuma. Sorry, I didn't.
Oh.
Sorry?
Foam.
Foam. Foam.
Oh, yeah. Thank you. So basically, I don't know if you have this kind of thing at home, but this is the very, very nice displays. And okay, this one is called nanocells display, and it's made with okay, this is a conventional display, RGB wavelength, and you can see that, okay, we have the blue is okay. And then you can see that between the green and the red for doing the RGB wavelength, we have these not really nice things right here. So the yellow is not well filtered, okay? Then with these kind of things, we will have nano emitters based on nanoparticles. In general, they are made with quantum dots, for example, and the quantum dots will emit the light at a very precise wavelength, okay? So it's much more better, and we will get nicer screens and nicer colors, and you can see here the difference in between both. And okay, this one has to be better. Second way of application is the nanodetector based on nanoparticles. So this is something we made in my lab, and okay, we define this kind of micro lens, and then we put a nanoparticle on the top of the micro lens. This is an objective of our microscope. So basically, we are able to see that with the microscope, and then we will be able to make right here, or just to put right here, 1 or 2 nanoparticles. So okay, in that case, there is nothing. When you shine light on that, you have basically nothing. Then we will put just 1 nanoparticle. You can see the nanoparticle right here, the white dot, okay? And if we shine light, we will see this peak, and this peak is corresponding to the absorbance and scattering made by this nanoparticle. And okay, we make some calculation. This is the black line, and you can see that the black lines fits very well with the experimental dots. And then we have here a dimer. Okay, you can see a nice image of the dimer. So there are 2 nanoparticles, and in that case, we have basically two peaks corresponding to the 2 modes. One mode when the light is oscillating in that way, and one mode when the light is oscillating with that way. Okay. And okay, the same, we make the calculation, and you can see that we have a very good agreement between both. Then using that, we will put some molecules on it and try to detect the molecules. How it works, the nanoparticles, okay, in that case, it's gold nanoparticles. When they are covered, or just when they are dealing with some nanoparticles, we will have a change in the refraction index close to the nanoparticle, and we will have a move. Whoops. I'm sorry. It's crazy right now. Yeah, because I put my arm onto my keyboard. So this is the reason why. So, and you can see that we have a shift of the peaks, okay? So we are able to detect the molecules. So we did it with the light in that way, oscillating in that way. So this is the peak corresponding to these blue things. And then with the light oscillating in that way, and this is the peak corresponding to these red things. Okay, and we play with a very, very small molecules called pyridine. And you can see that we are able to detect pyridine when the light is oscillating in that way. We are able to detect pyridine right here, okay? And in the case of this mode, we are able to detect it, okay, in between these 2, basically this one, okay? And when we make some models of the molecules onto our dimer, we are able to calculate the number of molecules. So basically here we have, something like 50 molecules corresponding to 4 zeptogram of matter detect through our system. And zeptogram is 10 to the minus 21 grams. Okay. So I can continue with anti-cancer, but I think I have to move because we'll go to the things. Okay, right now. And my last part, it's nanolabeling, an opportunity to safeguard archaeological artifacts. I guess that's the point for which you are coming today. So first, as you know, but I think that you know, there is or there are many traffics of archaeological objects. So these are things made in France, and you can see that a guy, we find all this stuff. So the guy made his own antiquities museum at home. Huh? So we have many issues, and we must protect the cultural property with a marking allowing first the identification, the management, and the security. At this time, basically, when you discuss with the people of the museum, you see that, okay, they put some, using this kind of marker, number right here, or then you can find this kind of thing, right? I guess that you know that much more than me. So the things I am trying to deal with is to encode several pieces of information in a transparent ink or varnish. And I want to put in my information the year excavation, the excavation sites, the museum of conservation, etc., etc. So how we will be able to do that? But first, I will present you a non-exhaustive review of the anti-counterfeiting marking techniques. So I will begin by the things we can find in the scientific literature. The first one is this one. So it's nanolograms. Okay. They are made that from nanoparticles. And then when you shine the light, you can find these dino at various with various color. We're able to do nano barcodes. So this gold, and then after the gold, you are able to do the growth of another material, then gold, another material, gold, and make like this some nano barcodes. You can see the example of nano barcodes right here, and we are able to encode, okay, 1111 or 11101 just by playing. So like this with gold, nothing gold, nothing gold, nothing, nothing, nothing gold. So means 11101. Okay. Then we have tag nanocomposites. And in that case, okay, we will have many things. For example, with these QR codes. So basically, you will be able to see the QR codes. Then we will have an embedded text in here. Okay, and then just by playing with the polarization, you will have all the QR code. With the other polarization, you will have the text, which is in the code. Then we have the radio frequency identification chips. Okay, these are rice, and the chips is the small black things right here. So it's very small, the things we have here too. And okay, it's possible to have in that case radio frequency identification, but okay. And then nanofingerprint surface analysis using laser authentication, the same. So you have a pattern in that case made with just a metal or a metal with a polymer charge with a luminophore, so something emitting light. And just by playing with things and with the polarization, for example, of these nice things, you will have this green butterfly or it's a blue alien, okay? And both are like this in the same image. The same then, just by playing with different nanoparticles in varnish, okay? And they are just playing in that case with magnetic field. By increasing the magnetic field, they increase the density of the nanoparticle, and then the light which is scattered is changing from blue to green to yellow and so on. And just by playing like this, you have these very, very nice things. Okay, yeah. This small tree, for example. And okay, in transmission, so when the light passes through the pattern, you have these nice things, and in reflection, you have these things. Okay, and the same right here. And then we have the already existing solution on the market. So the first one is called TrueTag, and they are doing some QR code on, in that case, some pills of drugs. But okay, this is micro scale. Then you have on this, okay, it's for drug too. You have here something, and they are just looking for the rugosity of the paper right here in these small bags. And okay, this one means, okay, they assign to this rugosity signature. Oh, whoops. And okay, in this one, because the rugosity will be different from one box to another signature with another code. Okay. And then yeah, basically here the same. There are okay, there are some bubble in resist. It's called in that case proof tag. And the organization of the bubble, it's completely random. And then okay, you have just to make an image before, and you know that this tag correspond to this bottle in that case, and the other tag will correspond to another bottle. Let's go to the nanoscale right now. So I think that you know smart water. Smart water are based on melts of emitting objects, and it's built of a melt of about 40 rare earth elements, and they will be able using that to create a code. So you have basically a green emitter, and then you have a melt of rare earth elements, which are, let's say, the signature of the product you want to protect. Then you have the Olnica things. And in that case, they are based the same. They are developing a rare earth-based molecular tracer, then can be embedded in the materials, in the product, or in the manufacture parts. And same way than smart water, they will use also fluorophores in order to detect the marking. And the last one is applied DNA science, sorry. And okay, in that case, they will offer a DNA marking, DNA tagging with specific fluorophore and so on and so on. But the problem is that you have to send the markers to applied DNA science in order to be able to read it. So it's really complicated. The the technology they use in order to do that is not easily deployable on for each policeman, each archaeologist, and so on and so on. So then at this time in French we are marking the things using these things. Basically, you have the French guide, the practical guide for the marking and identification of cultural goods. Okay, you have to use these nice things. So basically, yeah, Mitsubishi, BIC, and Digitrace, and things, they are permanent marker or paint or something like this. And then, you use that. Very nice. And basically, I will just show you these things is, these things is made from that. So basically organic pigment and inorganic pigment called carbon black, and they are, small carbon nanoparticles, And basically, this is how we are making an ink. So through the Nature project, I discuss with archaeologists and policemen and so on and so on. We try to define some kind of specification. And now where I am to create new things. So basically, we are able to play with nanoparticles and to arrange it on a surface. We are playing with quantum dots, with carbon dots, with scatterers, So we are able to create colors, let's say. And then by playing with this color and varnish, for example, here we put silver nanoparticle in a resist. And I show you here the Lycurgus cup. So here in transmission, so it's orange with some parts pink, and here in a reflection, in reflection, it seems to be green. And we have this kind of things. You have the same with stained glasses in the churches, for example, basically. And just because you have metal nanoparticle embedded into the glass. So we play with this kind of thing. So here it's, for example, in reflection and in transmission. They are gold in water. So it was the really beginning. And now we continue. We don't care about that. With much more complicated things. So we have nanoparticles. I will not give you the things of the nanoparticles and so on we used, but we are able to create real and new inks in pens. And then now we send these paints to Sabine Fourier. And Sabine now it's using our pens and our inks directly into the excavation sites. And we developed the detector, this guy. The cost of this guy is very, very limited, of about 100 euros. So it's possible for each excavation site to have this kind of things, and then to, it's possible to put the ink and then to detect the ink, and the ink will contain a specific code, and using this guide, it's possible to read the code. This is a very, very simple approach. In terms of security, I think that we are at this time at the level of smart water. Now we are testing in how our solution is working with time, with all the things we will find on the excavation sites. So dust, people which are moving your things and so on and so on. So that's quite complicated, but And then the ultimate things we want to develop will be these things. So by playing with the approach I shown you just before, so the Einstein one, let's say, we will be able to put these kind of things. So it will be another way to mark or to label the different archaeological artifacts, and then it will be possible to link these QR code to database. And I hope that by playing with this and with the other ink I mentioned, we will be able to protect and connect the archaeological artifacts to a database. So I think it's time to conclude for me. I just try to explain you how to develop some kind of solution. At this time, I think that maybe we have not really usable solution in order to be able to secure archaeological artifacts. So I think that we have a possibility to take these things. Then it's possible to using nanoparticles-based ink and varnishes to offer an unlimited range of effect, because I just show you optical things because it's easy to see with a screen, but we are dealing with magnetic effects and other effects, other physical properties. It's complicated to mention. And then by using this kind of guide, it's possible to link our nanoparticles to a database. And I have to thank you for your attention. And I have to thank now the French National Agency, which are financing the NOSE project. We are working on that with Sabine and with the lab of the French police. And I have to thanks all the colleagues from l'École nationale supérieure de police, le laboratoire ISOMA, and then the Nature and NOSE project, because with these and these guys, we now find a way to be able to protect in a better way the archaeological goods. And thank you for your attention.
So, thank you, Jérôme, for very interesting, fascinating, I would say, presentation, because there are a lot of brilliant ideas. And of course, being one of the persons that was also involved in Nature, I'm happy to see that there are such a nice and useful results coming from the project. If Irene has nothing to add, I would give the floor directly to Armando.
No, nothing on my side. Armando, the floor is yours.
Armando, so please, we're also curious to listen to your presentation. Thank you very much.
So thank you very much now. Thank you very much to Jérôme for the nice presentation. I would like to also thank in my personal behalf in the name of INOV for the invitation to do this, to lead this questions session. First of all, I would like to ask people that were listening if someone has something to ask. First of all, if someone wants to step in, please, now it's the moment. Otherwise, I will just start with some questions of mine, which I found quite interesting. So my first thing is, you're a physicist, right? And so what is the story of coming to relate physics and archaeology? You told us a little bit about this Nature project. Can you tell us a little bit about how did you come to this application?
Yeah, for sure. It's a quite not really long story. So we have a professor at the UTT, which is coming from the French police. So before becoming a professor, he was a policeman. So he came to me and he sent me, okay, I need a guy dealing with synthesis of nano things and able to some marking in order to participate with the School of Police in a project called Nature. I said, okay, I think that I'm the guy, and I will come. And so I was discussing with then policemen and archaeologists and so on. And I find this application quite funny. And for me, it's really a new world, I have to confess. Huh?
Okay.
Normally, I am dealing with a quantum effect at the nanoscale, so it's quite recreative, let's say. So I said, "Wow, funny! I will find a new way to apply my nano things because we are making a lot of nanoparticles. We are trying to understand the physical properties that how the energy will transfer from one nanoparticle to one molecule. Or okay, we're dealing with crafting molecules and DNA strain in order to be able to see if the gene is okay or not. So we are doing and
So basically, you were the right man at the right time, right?
yeah, very simple.
I think we have a question already from Alicia. Please, Alicia, unmute yourself and ask your question. Hello.
Yes, hello. First of all, thank you so much, Jérôme. Thank you so much, Armando, for this amazing and scientifically grounded presentation. And I actually have quite a specific question because as myself, I'll present myself shortly. I'm lecturing in various institutions in Italy and working in illicit trafficking for over 10 years and currently finalizing my PhD on the case study of Iraq at the University of Reading in the UK. And I have just a couple of months ago also issued the paper on the use of forensic traceable technology for marking archaeological heritage, specifically in Iraq, where over 500,000 archaeological artifacts in 5 museums were marked just 2 years ago. And I mean, I have no commercial connection, so I'm not supposed to be naming the company, but it's about smart water, so everybody knows the technology that was used there. And you concluded your presentation saying that there are no existing solution cannot help archaeological artifacts be protected. So I had a very specific question about this because the forensic technology was developed in the beginning of the 90s. Since that, it was used on marking various private properties and all kinds of things. And especially in the mid-2010 or something, it was used widely in the UK to protect cultural heritage, namely over 4,000 churches, because there was like lead roof epidemics in the UK. Then the pieces were stolen, churches vandalized. So there was really a epidemical situation. And then the Met Police approached the forensic tech and they have developed new solutions. So now we actually have almost 0 level. So the deterrence of this tech was really proven. Plus the war monuments over in the whole country were using very intensely this technology. And that was actually the impetus to use it in Iraq and Syria. In Syria, for security reasons, it didn't go further. In Iraq, it did go further. And namely, it's my PhD supervisor, Roger Matthews, who supervised the work. So few 100,000 objects in Iraq museum were marked, and 73,000 in Suleimania Museum, and 3 more museums in Iraq. So that just actually to understand why you say there are no existing solutions that could actually help archaeological artifacts, because we do have. And the question consists in what added value you see in nanotech. For me, it was very interesting because my paper has been just issued and I interviewed 42 law enforcement agents about their idea on crime deterrence of forensic technology. And the result was the unanimity in favor, and we have already used it in Iraq. So how do you personally and scientifically and how to say archaeologically wise see the added value? Because I'm not a chemist, I'm not a physician, but I was trying to understand the medium of the usage. So you use liquid and add nanoparticle. The forensic tech also uses liquid plus rare elements. So what is the added value and how you see the future application, where and in what exactly way? Sorry for the long question, but thank you so much again, both for the presentation and the answer.
Thank you, Alicia. Jérôme?
Yeah, thank you. No, that's a very, very interesting question. The fact is that the way the solution of smart water works, but it works, but basically with black light, I will be able to reveal the marking, right? And then, okay, that there is a more complicated marking into the things. So it works for the, let's say, a piece of museum, but smart waters will not be able at this time. The difference with the solution we are developing is that we have basically something quite similar to the thing of smart water. The difference is that we will give the detector to the archaeologist, for example, or to the policeman. Detector will be widely distributed because the price is very, very low. And we will be able to detect immediately the code. So the difference with smart water, you will be able with a dark light to see, okay, it's marked or it's not marked. And then you will have to send the artifact to another place in order to be able to decode the code. I'm right or not? The difference with the solution we propose is that it's very simple to apply. So at this time, we are trying to apply it on directly in the excavation site. And then without any more intermediate action, directly the policeman or the archaeologist will be able to detect and to know exactly from which site, which level or straight it has to be found, in which place during the excavation works of each years, okay, of the, I don't know, for example, if we are looking for new artifacts in Cyprus in 2022, and okay, at this time the excavation site was this site in that place, and at this level of stratigraphy, we are able to code all that stuff, and then it, even if there is no issues of stolen object and this kind of thing, just the archaeologist will be able to replace the object into the good place, good time, in order to reconstruct the archaeological history, if you want. This is the difference, basically.
Mm-hmm.
I don't know
Okay,
if
thank you. Yeah, you answered, but it's actually the same, because the same with the forensic tech, you have the database, you can mark the piece, and then the database stays both with the police and with the institution that is marking, and you can simply use the UV torch, which is also extremely cheap. So basically, all the principles are it's working on the same principles as the forensic technology for over 30 years. So I totally agree, but it's I recognize all the principles in this. So thank you so much for your answer.
Okay, so this brings me to another question, which is, can't you simply erase the marking? Very simply, you just figure out that the marking is there and you just wash the thing out or something like that? How does it work, Jérôme?
It depends. When I am discussing with policemen, they want that the marking stay for all the life of the object. When I'm discussing with the guys of the museum, they say that the marking has to be removable easily, but not so easily, but okay, we don't know. And so on and so on. I think that in the case of smart water, it's quite complicated to remove it.
Okay.
I think that the same, you know, I mean that depending on what we want to do, I can let the marking for all the life of the object or not.
Okay.
So it will depend on the kind of things. At this time, because of the museum issue, it's not possible to keep it. So we are dealing with solutions which are erasable. And but okay, it's for me, it's easier to develop a solution which is not erasable.
Okay.
Maybe Armando, we can take the chat, the questions in the chat. There are specifically two.
Yeah.
One probably is for Irène, since she is from École Française d'Athènes, coordinator of the project. Vanessa says, apart from the Nature project, what about exchanging ideas with other EU-funded research projects, for example, Aurora? And then Domonkos, thanks for the presentation and says, have there been any tests conducted so far evaluating the durability of nano inks, which is also a bit what Armando was asking a little bit. So Irène, maybe you can answer, and then Jérôme, we can leave you the floor, and then we wrap up this webinar.
About the Vanessa's question, of course, we really want to exchange with Aurora and like especially our sisters project Aurora and Enigma, whom we introduced at the beginning of this session, and like any related project at all, but especially our sisters project. This was not really possible at the beginning of our projects, like all our three projects, but now we hope to do it further in the future. And yes, related to the second question, I think the floor is yours, Jérôme.
Thank you. Yes, we are currently running tests in specific box with control of the humidity, with UV, with variation of the heat in order to be able to test our inks. And we applied inks in October, I think, if I remember well, in excavation sites. And we will wait for 1 year in order to see if we are still able to read our marking. So we will play with physical way in order to be able to mimic the whole life of the inks, if you want, and then we are playing at the same time in the excavation site in order to be able to to be in the real condition. Sorry.
Great, Jérôme, and great, Armando. Thank you very much. Maybe PG, I'll let you close the session, thanking everyone for these wonderful moments of conversation.
Yeah.
Thank you very much.
I see that there is still the end of your raised on. I don't know if it's still from the previous. Wonderful. So just to be sure to close the session without leaving anything, I joined the invitation that has been given by Irène in order to involve as much as we can our sister project, because it would be really fantastic if we can share and organize other events as the ones that we have just listened today. Thank you very much to Jérôme for the really astonishing presentation, very, very stimulating for this very new idea. Thank you very much. to Armando, because we know how we are taken in these days, and so we really highly appreciate that you provide your time to help the success of this event today. Thank you very much to all the persons that are also have attended this event. And of course, my best wishes for a happy Easter time, and hope to see all of you to the next event that will be organized for the ANCHISE Talk in the next month. Thank you very much. Bye.
Thank you very much.
Thank you very much.